So this video lesson is for Physics 12, Chapter 1, and it's day 2. We're going to finish off looking at adding vectors, probably look at the best method out there, the cosine and sine laws, and then we'll take a look at how to subtract vectors. So last day we looked at adding a couple of vectors together. We used the same two vectors twice. The graphical method was visual, fast, but not very precise, and the component method was precise, but not visual and not very fast. This method pretty much has everything. It's fast, it's visual, and it's precise, but it only works well with putting a couple of vectors together at a time. So a quick little review of some Math 11 here, the cosine and sine laws. These are on your formula sheet, so don't worry about having to memorize them. They're there on your formula sheet. The cosine law really looks like Pythagoras off the start, and then it's got this correction term that deals with triangles that don't have a 90-degree angle in them. Interestingly enough, if it is a 90-degree angle in your triangle, cosine of 90 is 0, and this whole correction term disappears and you're back to Pythagoras. So it's kind of like an exotic version of Pythagoras. And the angle theta is the one that's opposite this kind of lonely side that's all on its own in the story. So there's only one angle in that cosine law equation. For the sine law, mathematicians like to pair up the angles with their opposite sides. So they go capital letter for the angle and then small letter for the side. And the ratio of the sine of an angle divided by its side length, its corresponding side length, is a consistent ratio all the way around the triangle. So that can be super helpful. The cosine law is great if you know that you've got all three sides, sometimes called the SSS situation in math. Or if you know you've got a side, and then an angle, and then a side, like exactly in that order as you flow around the triangle's corner, sometimes called SAS. The sine law is great if you know an angle, and then a side, and then an angle, sometimes called ASA. And if you have a situation where it's angle, side, side, let me think about the letters for that, that's the ambiguous case. It works, but you have to be careful about it. Okay. Here we go. Same two vectors. Leave yourself, like we did last day, I don't know, maybe about 8 centimeters of room. And then if you could, draw yourself a little compass rose down here and we'll get started. Now, you don't need a protractor. You can just draw the vector in, just freehand, maybe with a ruler to get it straight, and say, hey, that was vector 1. It was 20 meters per second long, and it was at a 45-degree angle. And you just declare it to be 45 degrees. Right? You don't have to measure it and get it perfect. And then you go and maybe draw another compass rose in, just until we're really, really good at this. And then add on, head to tail, the next vector. Remember, it doubled back to the left, like a lot. Okay, more left than the first vector went to the right. And so there's the second one. It's 25 meters per second, and it's 30 degrees up from west, if I remember right, from last day. And those are the two vectors that we're going to add together. It's very visual, right? It's fast. Didn't take me very long to draw it. And now what I want to do is say, all right, the resulting vector is going to be this one here. It's going to be that one in green. Now I'm just going to go back and add this for a second. Don't add this to your picture. It's just going to waste your time. But this is what we did last day. Okay, last day we took a lot of time and we said, oh, well, that 20 goes 14 over and 14 up. And the 25 goes 21 over and 12 and a half up. And the 21 fought with the 14, but the 12 and a half cooperated with the 14. And we put the whole thing together to find out that that green vector goes like back 7 and up 26. We're not going to do that today. We're not going to take all that time. Okay, so that was just last day. We're going to dive right into this. But if you were to go to a mathematician, up in our math department, and say, hey, can you please help me with this triangle? They'd be more than happy to help you, but they want to know just information about the triangle. And they don't really want to talk about how it relates to the compass rose, how it relates to like north, south, east, and west. So if you could take this 45-degree angle and maybe do that little zigzag maneuver, with the Z shape, they're officially called alternate interior angles, we could see that up in here there would be a 45-degree angle compared to west. And that allows us to say, oh, between this blue side on the triangle there, we're going to have 75 degrees. That should help us find what's going on for that green vector there. We're going to ultimately need to know how long that green vector is, and we'd love to know its direction compared to the compass. The math people will tell you what the angle is, down in this little pocket down between the green and the blue vector down here. Maybe I'll just call that theta. But if the math people can help us find that theta, we can probably pretty easily find down here what the angle is compared to west. So let's zigzag that 45 degrees up into that pocket there, and now I can see that it's 75 degrees. And so a math person would say, oh, you've kind of got the SAS situation, a side, and then an angle, and then a side. And that's perfect for the cosine law. So here's the cosine law. One calculation is just going to be like done, and we'll know what VR is. Well, maybe two, because you have to take a square root. So when you first throw all that into your calculator, of course you double check to make sure it's in degrees. You get a really large number, you take a square root, and you're there. Again, I don't care whether you go 3 or 2 sig figs. You can call it 27.7 or 28. But it's very precise. You'll get those same numbers every time you do it, okay? Unlike that graphical method. Now for the angle, maybe I'll go with the sine of this theta, this little helping angle here, to help me find the angle compared to west. Sine of that divided by its opposite side of 25 is, and now my working pair, as I like to call it, I've got my 75 degrees, and I know that that now is 27.7-ish, 679 actually. So there's my working pair. I can use that to help me find this angle. So I go ahead and I do that cross multiplying, and then I inverse sine it, and I get 60 degrees. By the way, every time you do the sine law, you're in that kind of risk of the ambiguous case. It could be happening, not always, but it could be. So you kind of look at this 60 and go, is it 60 or is it the other one, which would be supplementary to it. So it would be like 120 degrees. There's no way this angle theta can be 120 degrees because look, you already got 75 degrees in the other corner. That'd be 195. You're way over budget on degrees. So we're safe. It's definitely 60. But that 60 is not really my final angle. I want to talk about the angle on that green vector compared to west. So I can look at all the angles on the line there. 180 degrees on a line, minus the 60 I just found, minus the 45, and that's going to get me my 74 degrees. So very quick, very precise, very visual. It's got everything, except it only works really well with 2 vectors at a time. So if there are a lot of vectors to add, we might end up going back and doing that component method. That wraps up all the different ways to add vectors together. Don't fight this cosine law, sine law method. Use it. It's actually very powerful. Okay? And so if you're like, I feel more comfortable with components, I could be faster with that. You know what? Practice a few of these, and you'll be actually quicker with cosine and sine law. Final thing to do today, now that we've spent 3 different ways doing addition, let's look at subtracting. And we're actually going to make this really simple. I'm not going to show you the way to do it. So all you've got left is to just add the opposite. Okay? There is actually a construction way, a little drawing way you can do it, but it's just as easy to say, you know what, take the one you're subtracting, the one after the subtraction sign, create its opposite, go the other way, and then just add. And then you've got all those choices for how to add. Here's an example where you can actually do some subtraction. Sorry, I should have put little arrowheads on these vectors here, on VI, VF, and on A. Missed that, but if you want to put those in, you can. It's a kinematics question, right? Sounds like it's right out of Physics 11, but it's more complicated because the initial velocity for this rocket is to the north, and the final velocity for this object or rocket or whatever it is to the east. So yeah, imagine it's a rocket, right? So here, I'll tell you the backstory while you're writing that out. There's a rocket just coasting through space. The engines are off, and it's going 12 meters per second north. The astronauts, they fire up the engines, right? She runs the engines for maybe 4 seconds, right? And then after shutting them off, they're coasting at 5 meters per second to the east. And during those 4 seconds, I'd like to find the acceleration for the rocket, okay? The average acceleration that it took to get that change in velocity. So this is where you could do that whole VI, VF, DAT kind of table we would have done in Physics 11. Think about what equation would be great. The one without D, right? That one that says VF equals VI plus AT. And if you rearrange it, you basically get to here. You know, some people like to say, oh, it's change in V, delta V over T. And other people say, well, you know, if you take VF equals VI plus AT, and if you go ahead and move the VI and then divide by T, yeah, either way, you're going to get to here. You can either write that as a delta symbol, that means subtract, right, means change, or you can explicitly write the subtraction. And here we are. We now have to subtract some vectors, but we can do that by adding the opposite. So instead of subtracting VI, instead of subtracting 12 north, I can change that to add. if I go with the opposite of 12 north? Well, that would just be 12 south. So that's going to be my plan. Let's do this question by going VF plus negative VI, right? We'll add 12 south, and then eventually we'll divide by time. I should tell you that the dividing by time part's the easiest part. It's this numerator that's going to take us the most time. So let's see if we can get that to work. So VF is 5 east, and then we will add, head to tail, connecting on the ends, the opposite of 12 north. So that would be 12 south. So I'm technically doing components here. It's just that I don't have to resolve these things because they're already resolved. 12 south is just simply 12 south with nothing sideways. Okay. So we need to find the resultant for doing this addition, which we're using to fake a subtraction, and we need to find the angle. And this is a really nice one. It's all right angle trigonometry, so it goes pretty fast. Pythagoras offers you a beautiful, nice 13. It's one of those math people call them Pythagorean triples. And then we inverse the tangent, right? We do arctan, officially it's called, and get 67 degrees. And so the numerator, I haven't finished this question, but just this numerator up here, that's going to end up being 13 meters per second. Okay, this is the delta V. 13 meters per second, 67 degrees south of east. Almost done. I just have to divide by this 4 seconds. When you divide by the 4 seconds, here's where it actually gets the name scalar. It cannot change the direction. So we're not going to touch this 67 degrees south of east. Just leave that alone. But we can scale up this number. We can make it bigger or smaller. And dividing it by 4 is going to make it smaller. So that's all we do when we divide by 4. We only work with that magnitude part. And the 13 divided by 4 becomes a 3.25. Hey, it's an acceleration. So it'll be meters per second squared. And it's at an interesting angle. That's the direction you'd have to fire the rocket thrust, right? 67 degrees south of east in order to create that change in velocity. So there's a nice little example of subtraction. We're going to fake it, turn it into addition. So any vectors that are after a subtraction sign, we'll just change to add the opposite. You can even do that with components too. You can subtract vectors with components if they're messy. You'll just have to say, okay, when I'm doing my work with the components, putting the components together, make sure you subtract those component values. And that finishes up our second lesson for Chapter 1.